number 4, we have a forest fire spreading in a circle, so that's going to be important, with radius changing at a rate of 5 feet per minute. When the radius reaches 200 feet, at what rate is the area of the burning region increasing? So we're going to draw our picture. We have a circle. I know I just well, that's a bad circle, but it's more of an oval. I'm just trying to make it flat. It's changing at a rate, our radius is 200 feet. I'm going to go ahead and draw that in. Our R is 200 feet. Our rate of change of our radius is 5 feet per minute. Double check, should that be positive or negative? Our fire is spreading in a circle with that radius changing, so it should be increasing. And then that would make the area of the burning region increase as well. So dA dt is equal to blank. Okay, so our formula that will relate this, area and radius of a circle, is A equals pi r squared. This is definitely a formula you will need to know. Step 3, we're going to take our derivative, dA dt equals 2 pi r dr dt. Step 4, I'm going to go ahead and plug in. My dA dt is what I'm looking for. My r, my radius, is 200. My dr dt is 5. So my dA dt is 2,000 pi. And don't forget your units. This is area over time, so that would be feet squared per minute. And don't forget your smiley face. Okay, number 5. At noon, ship A is 100 kilometers west of ship B. Ship A is sailing south at 35 kilometers per hour, and B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Okay, so let's just start at the beginning. Ship A is 100 kilometers west of ship B. We know ship A is sailing south at 35 kilometers per hour, so that's dA dt. And ship B is sailing north at 25 kilometers per hour. That's my dB dt. We can figure out signs and stuff in a minute for that if we need to. We want to know how fast is the distance between the ships changing at 4 p.m. So what we're actually looking for is the distance between the ships, not like vertical distance or horizontal distance, but the true distance between the ships. So we're actually looking for this diagonal here. And so what we want to think about is, instead of just like a horizontal line with 2 vertical lines there, we're actually going to make this into a triangle. And let's label the sides X, Y, and Z. So we won't even actually be using the A and the B here. So we know the X is 100. And that's always going to be 100 because I know they're 100 units horizontally from each other. What's changing is their vertical distance. So I know that the formula I can use here is 100 squared plus y squared equals z squared. If I need to find it at a certain time, I can do that. So let's take a look. That's all step 1, drawing our diagram. Number 2, that's our equation we're going to use. Step 3, we want to take this derivative. Derivative of 100 squared is just 0. So we have 2y dy dt equals 2z dz dt. Now, we haven't talked about any of those rates yet, so let's go ahead and look back over at our rates. dz dt is what we're trying to find. How fast the distance between the ships is changing. What we want to know then, we'll need this dy dt. So we know ship A is sailing south at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. So each hour, they would be the sum of that apart. So they would be 60 kilometers per hour apart. So that is their vertical rate of change. And so in order to figure this out at 4 p.m., we knew that this was at noon. So at 4 p.m., they would have sailed 240 kilometers apart vertically. So then if I want to figure out how far their actual distance is, I can go ahead and plug in that 240, and then I can solve for my z. If you solve for that, you will get 260 for your z. So I can go back here to step 4 and plug those values in. So my y is 240. My dy dt is 60. My z is 260. And my dz dt is what I'm trying to solve for. Then I can go ahead and simplify. So on the left, I have 28,800. Should definitely be using your calculator on this. Equals 520 dz dt. Divide both sides by 520. Oh, I guess it's not step 6 yet. Getting ahead of myself. That's the smiley face. If I go ahead and simplify that to a decimal, we always want to use 3 decimal places. 55.384 kilometers per hour is my dz dt. And let me go back and say we always want to use 3 decimal places unless it tells us some other value, some other place to use. Okay, let's take a look at this question from the 2002 AP exam. It's a great year to take the AP exam. It's actually the year that I took the AP exam, probably before most of you were born. But anyway, so we have a open right circular cone. Here's the diagram. It's nice they gave us the diagram. It tells us the height of the container is 10 centimeters and the diameter is 10 centimeters. And water in the container is evaporating so that its depth h is changing at the constant rate of -3/10 centimeters per hour. So that tells me h is changing at that rate. I'm going to go ahead and just label that. That's dh dt. Notice it also gives me the volume formula here. So that formula is given to me. That will be important. A asks us to find the volume V of the water in the container when the height is 5, indicate units of measure. And so we'll have to do a little bit of thinking about this here. We need to figure out what the radius is when the height is 5. And so there has to be some relation here. And so if we take a look at the radius of the whole cone, not just of the water, that would be 5 because it's half the diameter. And so what's happening here as I fill up, my height and my radius always have to be proportional to the height and radius of the whole cone. So there's actually some similar triangles happening here. So my radius over my height always has to be equal to 5/10, no matter where I'm at within this cone. And this is an important property of cones to keep in mind on these types of problems. So in other words, that means that my radius is always half of my height. If I simplify this, this is 1/2 and then multiply by the height. So for part A, when I want to find the volume of water in the height when our height is 5 centimeters, when h is 5, that means the r is 5/2. So my volume is going to be 1/3 pi times 5/2 squared times my height, 5. I can leave my answer right there as long as I put my units on it. And so for volume, and these were measured in centimeters, volume is units cubed, so I'd have centimeters cubed. For part B, it asked me to find the rate of change of the volume of the water in the container with respect to time when h is equal to 5. So we're going to use this formula here. And so what we're going to do though is, because we have this relationship between r and h, we're going to go ahead and use that to begin with. We're trying to find rate of change of volume of the water. We're given dh dt, so we only want to have v and h in our formula. So instead of r, we can replace the r with the 1/2 h. So that will just make it easier for our derivative and for our evaluation. So our r is going to be h over 2. And then times h there. So if I simplify this, I'd have h cubed times pi all over 12. Don't forget to square that too. So now when I take my derivative, it's going to make it nicer because it's only one variable. So I'm going to have 3h squared pi over 12 times dh dt, which is just h squared pi over 4 dh dt. Now I want to evaluate that when my height is 5. So dv dt when my height is 5 would be 5 squared pi over 4 times my dh dt, which was given to me, negative 3 over 10. And my units for this would be, this is rate of change of volume, so it's going to be centimeters cubed over hours. So again, where that comes from is the 5 squared, that was centimeters squared, and then this was centimeters over hours, so I get centimeters cubed per hour. That would be my answer for B. For part C, it says, show that the rate of change of the volume of water in the container due to evaporation is directly proportional to the exposed surface area of the water, and then what is the constant of proportionality? So if you're trying to say that you're directly proportional, that just means you're equal to but times a constant. So the rate of change of the volume of the water, that means dv dt. So we already found that that before was this value right here. So I'm going to rewrite it a little bit, 1/4 pi h squared times dh dt. We want to show that that's proportional to the exposed surface area of the water. The surface area of the water would be pi r squared. So we have to show that this is equal somehow to pi r squared. Let's go ahead and plug in the dh dt, 1/4 pi h squared times our negative 3 over 10. So we have negative 3 over 40 pi h squared. Now, it is asking about the exposed surface area of the water. If we looked back up there again, the exposed surface area is a circle. So we're trying to make it as a multiple of pi r squared. Our equation right now has an h in it, so we're going to translate it back into r's. That has to be negative 3 over 40 times pi times our height is 2 times our radius squared. So we get negative 3 over 40 times pi times 4r squared, which is negative 3 over 10 times pi r squared. So what you should notice is that this pi r squared is that area formula for our circle. So this is negative 3/10 times the exposed surface area. And so that number, the negative 3/10, is the constant of proportionality.